All right. Well, welcome to those who braved the severe weather to come here for the seminar in person, and welcome to those of you online joining us today for the next installment of our Sustainable Energy Seminar. If this is your first time joining our seminar series, my name is Scott Williams. I'm the Research and Education Coordinator at the Wisconsin Energy Institute. And the Sustainable Energy Seminar is something that we do every other week here at the Wisconsin Energy Institute to bring different faculty members, researchers who are doing from a variety of disciplines, whether that's science and engineering or social sciences and humanities, to learn about the many ways that they understand energy challenges and develop sustainable solutions. This seminar is also part of a class for students in the undergraduate Engineering for Energy Sustainability Certificate, as well as the Master's in Sustainable Systems Engineering. If you have a question online, please use the Q&A box. There's also a live caption feature. Just click on the show captions button to turn that on. We'll be alternating between in-person and online questions for the Q&A portion. So feel free to post to the Q&A at any time if you do have a question. We'll try our best to get to it. And with that, our speaker today is Luca Mastropasqua, who's an assistant professor in mechanical engineering here at UW-Madison. And he leads the Hydrogen and Electrochemical Research for Decarbonization, or HERD lab. The lab's research focuses on electrochemical energy conversion devices and systems for decarbonized and zero-emission power generation, energy storage, and industrial manufacturing applications. Their goal is to characterize and explore the fundamental physical and chemical processes of electrochemistry and thermodynamics to discover new concepts, advance new devices, and conceptualize novel process integration and scale-up systems to final applications. So Professor Mastropasqua, his presentation today will provide some examples of those electrochemical devices and how they can be utilized for sectors that we tend to think of as harder to decarbonize as we're transitioning to clean energy sources. So welcome.
Great, thanks for the introduction, and good afternoon, everyone online and here. Today I'm going to talk about high temperature electrochemical devices, especially for decarbonizing industry and manufacturing processes. The outline of my presentation is as follows. So I'm going to talk about why do we need electrochemical systems, devices and systems to decarbonize these applications. And I'm going to give you the example specifically for hydrogen generation, which is, you'll see, one of the main energy carriers that I think we will need to decarbonize one of the some of the hard to abate sectors. And I'm going to give you the specific example of steel decarbonization. And then I'm going to end with a few examples related to electrochemical synthesis of products, of fuels, of commodities that we use extensively in our society, but we still need to find a way to decarbonize. And one disclaimer is that the story that I'm about to tell is a very, it's a complicated story that has a lot of plot twists, not a very linear plot. So if you, there's not going to be one single solution for any of these things that I'm going to tell you. So the result is unexpected, and that's why we still need a lot of research to figure this out. So the motivation for all this is that electrification of processes can be an economic way of defossilizing our society. And I say defossilizing and not decarbonizing because really you'll see a lot of these processes will still need carbon, or will still need molecules that are carbon-based to work, to perform all the processes that we do today. So the main goal here is really to remove fossil fuels from these manufacturing processes and industrial processes, and produce the same type of feedstocks that these processes need in a renewable fashion or in a low carbon fashion. So electrification is one way, and the reason why electrification could be one of the ways is that we've seen costs of solar and wind coming down very rapidly in the past few years. So you see that on the left-hand side, utility scale PV of different technologies has decreased very rapidly, and similar thing can be seen for wind on the right-hand side. And I like this chart on the right-hand side because it shows the power purchase agreements for deploying wind resources as a comparison to the gas prices, which is the dashed lines. So today, deploying wind resources or solar resources is really equal, if not more competitive than purchasing gas. So there is really an economic push to use electric-based processes to do what we currently do with fossil fuels. So the economic argument is an argument that motivates the transition from fossil fuels to electrification, in addition to the climate change emergency. So that is an additional argument that the transition to renewables and cleaner processes is not only economically better, but also environmentally more sustainable. So the question at this point becomes, can we electrify everything? And what are the processes that are the most difficult to decarbonize or defossilize? And can we do everything can we decarbonize our whole society with electricity? So on the left-hand side of this slide, you see the greenhouse gas emission by sector. And you see that most of the greenhouse gas emissions come from energy use. And the big slice of that energy use and CO2 emissions comes from energy use in industry, which is the top right part of this pie. So the energy use in industry, most of it is used in iron and steel, in chemicals production, oil refineries, cements, plastics, paper, glass. These are the very hard, the heavy industries that use a large portion of the energy in our society. And similarly for transportation, the majority of transportation CO2 emissions come from road transport. And don't confuse road transport with cars. Road transport is mainly heavy duty trucks and buses and trains, diesel trains. So in addition to that, then we have the even more difficult sectors like aviation and shipping. So I like the chart on the right because this is a projection on to 2040 by the International Energy Agency that says that according to our prediction or our models, in 2040, we will have basically decarbonized the power sector and partially the buildings sectors. So we will have electrified most of it and basically decarbonized the power sector and our residences. The two sectors that will still have a lot to work on are transportation and industry. So this tells me that really currently today we have very few options to decarbonize these sectors, or even the technology that we need to use to decarbonize those sectors is to be developed or even invented. And so the future society that will be able to decarbonize hard to abate sectors is one that I think, as reported in this paper, uses a lot of renewable or low carbon energy carriers. So in this figure, you see that there are services like aviation or like cement production or steel production that use all these flows of molecules, including hydrogen, including some hydrocarbons, the purple line, some ammonia, some chemicals, and CO2, the red line. So those are flows of molecules of feedstocks that we will need to use to as input streams to some of the hard to abate sectors that we need to decarbonize. So again, the question is, what is the role of electricity? How much electricity can help us to decarbonize these hard to abate sectors? So here are some examples. So here you have cement production. So in order to produce cement, currently we use furnaces that go up to 1800 C, and we need natural gas or coal as a source of energy in the furnaces, in the kilns. We need electricity to power some of the auxiliary processes in the kilns, and we need limestone. So limestone is one of the main streams, material streams, and that, if you don't know the formula of limestone, has CO2 in it. It's CO3. So it's so that that input stream, if you oxidize it or if you convert it in the way the kilns do today, releases CO2 because it contains carbon and oxygen in the initial molecule. So even if we didn't use natural gas or coal to power the furnace, to heat up the process, we would still emit CO2 because the nature of the process is such that it would emit CO2. Steel, it's similar. So steel, it produces, we need furnaces that go up to 1200, 1400 C. Currently, they use a lot of coal and natural gas to increase the temperature of the furnaces. We need electricity. We need iron ore, of course, as an input stream. But we also need carbon. Carbon is another input that is needed to produce steel because the final product is carbon steel. It usually has between 1% and 3% mass of carbon in the final steel product. If we didn't have that carbon, all the downstream steel making processes would have to be reconfigured, completely redone. So the carbon is important in the steel product, and so in order for this transition to be even feasible, we need to be able to remove or replace the furnaces with processes that can produce similar products. And then the last example that I bring here is chemicals and fertilizers. So for the production of ammonia, for example, we need the Haber-Bosch process that operates around 450 C, and of course needs natural gas and electricity and nitrogen. The natural gas that I report here is both needed for increasing the temperature of the process, but also as a feedstock to produce hydrogen. So ammonia is NH3, and the hydrogen content in ammonia comes from natural gas. So the natural gas that you see here in this is really used as a source of hydrogen. And this is to produce ammonia. Ammonia is then used as a feedstock itself to produce fertilizers, for example. And to produce fertilizers, you need urea, and urea has carbon. So that means that you need to add carbon to ammonia. So if you want to produce fertilizers and produce a product similar to what we have today, there must be somewhere in the process a point where you inject carbon with ammonia to produce urea. So the point of this slide is really, we can use electricity to do a lot, but we will still need a lot of input streams or molecules that will need to be produced in a low carbon fashion, despite the fact that these will contain carbon in the chemical form. Here the electrochemistry comes in. So the proposition here is to completely change the paradigm of how we produce chemicals, how we produce commodities. So the paradigm change is from business as usual, where we use fossil fuels to power our transportation sector and power our manufacturing and industrial sector, with no or minimal improvement in energy efficiency, to one that produces energy carriers, sustainable energy carriers. And energy carriers, in what I do for my research, are produced from renewables, so either solar or wind, via electrochemical processes, so using reactors that are called electrolyzers, or that use electricity as an input, electricity and heat, renewable heat as input, to produce hydrogen, which is one of the main energy carriers, or other sustainable energy carrier or synthetic energy carriers that can be used as a replacement to fossil fuels for the processes that I talked about earlier. And then the even longer term transition would be to come up with new electrochemical processes that could do the production of commodities directly in one single step. So what I've called here electrochemical manufacturing. So imagine like an electrochemical reactor that would take renewable heat and electricity and directly carbon, limestone, iron ore, or nitrogen, similarly to the processes that I saw that I explained earlier, and directly produce steel, ammonia, clinker, cement as a commodity. So this is kind of the very long term and not commercially ready pathway yet. But this is the research area that I'm focusing on. So now I'm going to give you one more detailed example of hydrogen production using high temperature electrolysis coupled with high temperature heat sources and renewable electricity. So to do that, I first introduced the device, which is a solid oxide electrolyzer. This is one electrolyzer technology that can use electricity and heat, and the heat portion is important, and I'll come to that point in a little bit. So a solid oxide electrolyzer is comprised of two electrodes, an anode and a cathode. The cathode receives steam as an input. So you evaporate water and you produce steam, and that is your input to the cathode side. The anode side receives air as an input. So again, at high temperature, these systems operate at around 750 C. So you have to increase the temperature of your input streams. The steam is then split using input electricity, which comes from your wind farm or solar PV, into hydrogen and oxygen. And the oxygen is then transported through a membrane, which is your electrolyte in this case, and recombined on the anode side. So the anode will produce an oxygen-rich stream at the output. And the cathode at the output will have hydrogen, pure hydrogen, plus some unreacted steam. That unreacted steam can either be recycled back to the input or simply condensate out, and you would have a stream of pure hydrogen. As I report here, these reactions occur with the addition of, or can occur with the addition of heat. So heat could be important to increase the efficiency of these processes. This is, on the right-hand side, just another sort of schematic or picture of how one of these look like. They really look like sandwiches of layers where you have channels of gas streams coming in and out of the streams, and in the middle you have the three active layers, the two electrodes and the electrolyte. And at the bottom here you can see these are some of the cells that we use in the lab for research purposes. So these are smaller scale cells. So from a thermodynamic perspective, the reason why heat is important is that if you look at the reaction of water splitting, so just look at these two bars, the delta G of your reaction decreases as you increase temperature. That means that the electric input to perform the same process, if you perform the same process at high temperature, you would consume less electricity, which is the delta G in this figure. That happens with an increase of delta H of the whole process, because you compensate the decrease in electricity with an increase in heat, in the heat consumption. So the T delta S portion of this bar increases at high temperature versus the low temperature, which means that you will need, use more heat to perform the same reaction while you decrease the electricity. So this is useful because if you have high temperature heat or waste heat from an industrial process that you can use, then all of a sudden you are decreasing the amount of electricity from your PV or wind farm to perform the same process. Another, without going into all the maths here, the chart here on the left shows that these devices can operate at different thermal balance conditions. So if you operate at low current, so on the left-hand side of this chart, the black line shows a positive heat to the system. That means that the system is consuming heat. It's an endothermic process. Okay, so the water splitting reaction is an endothermic process. So at low current, the system can consume heat. If you increase the current, your electric circuit will start increasing, it will start producing more and more heat for Joule heating processes. So your endothermic reaction will be compensated thermally by the Joule heating. And so there is going to be a point, which is over here, at a certain current, where the system becomes thermoneutral. So you have all the endothermic processes compensated by the Joule heating processes. So that is that's so-called thermoneutral current or thermoneutral voltage, which corresponds to that current. And beyond that point, the system becomes exothermic. So the Joule heating processes will more than compensate the endothermicity of the reaction, and so the system becomes will start producing heat. So for thermal integration, it's really more interesting to work at in endothermic condition, because you can take advantage of the integration with renewables, with especially renewable heat. So this plant layout is one that we studied, where you have the integration of a solid oxide electrolyzer with a solar plant that produces a concentrated solar system that produces both electricity to power the SOEC and high temperature heat. So these are parabolic dish systems like these ones that have a micro gas turbine on the focus of the parabola that produces electricity, and others will have other dishes will have receivers that will simply heat up the steam and supply heat to the SOEC. So the system, as you can see here, will take steam as an input and will produce two streams of pure hydrogen and pure oxygen. Then the two streams will, you can recover heat from the two streams using heat exchangers, and then using simple sort of gas compression units, you can store hydrogen and pure oxygen for whatever downstream process you need. So The efficiency here of the process is really a function of the operating condition of the SOEC. So this figure is a bit complicated, but it basically shows that at different current density, there is a different thermal balance of the SOEC because of what I explained earlier. Some conditions will be in endothermic mode, some conditions will be in exothermic mode. And in terms of efficiency, so this is sun to hydrogen efficiency. Depending again on the operating condition, we can achieve 16 to 18% efficiency. So all the energy from the sun will be converted. 17% approximately of the energy of the sun will be converted into hydrogen final product. This compares with other forms of solar hydrogen generations as follows. So if you had, for example, a polymer electrolyte membrane fuel cell that operates at low temperature plus a photovoltaic system, this usually reaches 10% of sun to hydrogen. Others like solar tower plus thermal energy storage will be a bit lower. So the system that we've discussed now with the dish really can achieve higher temperature, so can achieve a higher heat input to the SOEC, and that really helps with the sun to hydrogen efficiency because you use less electricity per unit hydrogen at the end. These are sun to hydrogen efficiencies that are across the whole year of operating the unit. And these are, so you can see a video of how we simulated the shading profile of the solar field, assuming that we had a direct normal irradiation from a specific location, as follows for, this is the month of July, but the simulations were done for the whole year. So you can see the profiles of electricity from the CSP unit and the heat input from the CSP unit. So that is, the heat input is again, what makes a difference compared to other solar to hydrogen technologies. You can see here that we had also some electricity from natural gas and heat from natural gas. This we did that additional simulation to take into account if there was some condition, some days during the year where the sun was not available or not enough to power the electrolyzer. Then we had the microgas turbine hybridized to burn natural gas as well, but that was not a requirement. So as you can see, if you couple electrochemical technologies with renewables, you have very fluctuating operating profiles, as I've shown in the previous slide. So my question at that point was, can these systems operate for a long time in using these very fluctuating input conditions without degrading their performance? So this was a test that we did in the lab using a variable input. So you see the current, the cycling current in this figure that we asked the electrolyzer to operate at. So for 3,500 seconds, that was the profile, and then we repeated that cycle for 3,000 hours. So the figures on the right report the different cycles in terms of stack power and voltage. So basically, we operated the SOEC for a long time using extremely variable fluctuating profiles of input current, and then measured the voltage to see if that was degrading as a function of time. And this was surprising because we didn't see any really measurable voltage degradation using these tests. And these are, this picture here is from a commercial unit. So you can purchase this today. And this system certainly was not designed to follow renewable electricity. So we were pleasantly surprised to not see a appreciable voltage degradation for this type of demanding operating condition. And this, by the way, was also tested in fuel cell mode for data center applications. So data centers also have a very extremely fluctuating profile of input current. And so we wanted to power data centers with this fuel cell. And that was another sort of important outcome of this. We could power very fluctuating power loads without having major degradation. The title here, though, says that we need operando analysis tools. And that's what we did afterwards. So we looked at how these systems operate in very fluctuating conditions and used operando analysis, operando characterization. So these are, on the left-hand side, are what are called electrochemical impedance spectroscopy data that give basically a picture of the health of the cell. So you measure the voltage using an input of fluctuating current, and the cell will give you as an output a voltage response with a certain amplitude and frequency. And then after some math, you do some signal analysis, and you come up with those Nyquist plots that are the input for the electrochemical impedance spectroscopy analysis method. So we took these data, these electrochemical impedance spectroscopy data, and we created a machine learning model that was able to tell us whether that spectrum was from a healthy cell or a defected or faulty cell, and which fault was associated to which spectrum. So on the right-hand side, you see examples of the results of the machine learning algorithm testing many of these spectra. And if the predicted value was within was 1.1 for this method of fuel maldistribution and 0.05 for this other degradation method, oxidant leakage, that was in the sort of healthy condition. Beyond those, all the other values were for faulty cells. So the method was really helpful to get electrochemical impedance spectroscopy data on steady state operating devices, give this as an input to a machine learning algorithm, and then that was really able to tell us if the cell was healthy or not. All right, so this was hydrogen production, which again is one of the main building blocks and main energy carrier for some of these hard-to-abate sectors. Now I'm going to talk about one specific application, which is steel. So steel today is produced using what are called blast furnace, basic oxygen furnace mills. So the process takes iron ore, it brings it to a pellet size, it feeds it into a blast furnace that uses limestone, coke as a input feedstock. And that is not just, again, as I mentioned at the beginning, not just to increase the temperature of the unit, but it's also a mechanical support. The coke, because it's a solid product, it helps the mechanical stability of the fixed bed reactor, which is the blast furnace. So it's really hard to remove coke because it's not just a fuel source. The blast furnace produces metallic iron, and then it goes into the steel making process, which could be an electric arc furnace or a basic oxygen furnace process. So this is the way more than 70% of the steel that we produce today is produced. And it's really energy intensive. It consumes about 20 gigajoule per ton of steel, of primary energy. And it's really carbon intensive. It emits around 2 tons of CO2 per ton of steel. So in order to decarbonize this process, there are really 2 methods. Either we keep the same production process that I just explained, and we perform carbon capture and storage. So we place a system that removes carbon from the flue gases, but the manufacturing process remains the same. Or we need to change process. We need to come up with new alternatives to still making routes. By the way, the first method, the carbon capture process, we also looked at that, and it's reported in this publication, and it is one of the viable methods. There is certainly an economic aspect to consider. Well, this is a more detailed mass and energy balance of the actual blast furnace. And I'm not going to go through a lot of this, but the main message that I want to bring here is these plants are extremely complicated, are extremely large, and changing the manufacturing process is, or changing how one of these boxes operates, it's really hard because they are all connected, and so you either use something that can be plugged in or to the conventional process like carbon capture and storage unit, or it's really the other option is to change process. Here we looked at the carbon balance, so which are the units that emit more CO2 in a conventional unit, in conventional steel plant. And you can see that the biggest is the power plant. So each of these units, each of these steel plant has its own power plant to power the manufacturing process. So the power plant is usually not a very efficient power plant. It's a steam cycle that operates like 30% efficiency. So it emits, percentage-wise, emits a lot of CO2. And then the others are the coke production process. Again, coke is very difficult to eliminate. And the blast furnace. So the blast furnace is this process here. So we looked at carbon capture and storage solutions, and it is possible to apply carbon capture and storage downstream one of the blast furnace steel mills. But again, you have many carbon sources, many flue or many stacks in a steel plant. So that means that each of those need to be taken and the CO2 abated from those. So our proposal was to change process and use what's called a direct reduced iron process, so or DRI. And this is not a completely novel idea. DRI is a fluidized bed reactor, which uses a reducing gas like hydrogen or CO, or a combination of those, to reduce iron ore. So iron ore is fed here at the top of the reactor, and as it falls down the reactor, it is reduced by the reducing gas stream that it's fed at the bottom. So the oxygen is stripped away from the iron ore. And at the bottom of the reactor, you end up with metallic iron. And then you can just add carbon to produce that carbon steel that I mentioned at the beginning. This process occurs at relatively high temperature, 1100, 1200 C. And again, if you are able to produce the reducing gas in a sustainable way, then this process will not be as carbon intensive as the blast furnace gas. So the reactions are reported here on the left. And really what you need is input hydrogen and CO that are produced in a low carbon fashion. I'm going to skip this for sake of time. So the process we proposed uses an SOEC that takes the top gas or exhaust gas of a conventional DRI furnace. It preheats that gas and it feeds it to the cathode of the SOEC. So remember, the cathode is where you feed the steam in a conventional SOEC. So that the top gas stream is relatively rich in steam, and there is some hydrogen in that composition. So the SOEC, what it does is converts the steam to produce a hydrogen-rich stream. That hydrogen-rich stream can be sent back to the DRI furnace after some waste heat recovery and preheating as a reducing gas. So this gas here at the inlet of the furnace will be a hydrogen-rich gas that is produced using water splitting, using electrolysis. And of course, if you use wind or PV resources to power the electrolyzer, that becomes a renewable hydrogen. On the right-hand side, you see the energy and emission performance of this system. So we looked at, of course, many different configurations, but if you just look at the one on the left-hand side, the primary energy consumption of this process is around 8 gigajoule per ton of DRI. And if you compare it with the number that I told you at the beginning, the conventional blast furnace case consumes around 20 gigajoule per ton of steel. So we are reducing the primary energy consumption by more than half. The emission performance, it's around 18 kilograms of CO2 per ton of DRI. And this also is a very large reduction compared to the blast furnace case. The blast furnace case emits around 2 tons, so 2,000 kilograms per ton of steel production. This emits 2 orders of magnitude less. Of course, the point here is that we need to power the electrolyzer with pure with 100% renewable electricity. Okay. All right, I'm going to conclude with just a couple of slides on synthetic chemicals produced using electrochemical methods. These are very low, these are not commercial technologies, but these are the things that I think are going to be the most promising ones to decarbonize the chemical industry. So there are these set of electrochemical technologies that use proton conductors ceramics. These are materials that operate at relatively high temperature, around 400, 500 C, and they conduct protons, hydrogen atoms, ions, sorry. And they can, with these, we can do a series of things, including, for example, as simple compressors of hydrogen. Increasing the pressure of low pressure gaseous hydrogen to high pressure gaseous hydrogen, or similarly for steam. But the things that we'll need that are sort of more interesting in terms of decarbonizing chemicals is you can hydrogenize or dehydrogenize organic molecules. And the hydrogenation and dehydrogenation processes are what oil refineries do all the time using steam reforming or natural gas. So these are processes that we can convert into electrochemical processes, and that could replace what oil refineries do today. So one example is the production of ethylene. Ethylene is one of the most used chemical in society because it is used as a feedstock for many chemicals that downstream. So this study takes ethene and produces ethylene using one of these proton conductor cells. So it dehydrogenizes ethane. So it removes hydrogen from ethane. It produces ethylene, and on the other side of on the cathode side, it produces pure hydrogen. So using the selective membrane, the electrolyte that can transport pure hydrogen ions, you can selectively remove, so dehydrogenize an organic molecule like ethane in this case, and produce ethylene in a very selective fashion. One of the main drawbacks of thermochemical processes is that despite the fact that they operate high temperature, and this is sort of summarized in these figures, if you operate at very high temperature, so the red dots, the conversion of your feedstock can be very high, but the selectivity of that process is usually not very good. You convert a lot of your feedstock, but you cannot really target which product you want to produce. So the selectivity can be low. So because electrochemical devices use current as input, that can be used to sort of tweak and control the selectivity, of course, with the appropriate catalyst choice. So this to me is one of the main advantages of electrifying chemicals production, because you can reach a better trade-off between conversion and selectivity of products. This is another example of steel production. So similarly, you could imagine having iron ore fed directly to an electrolyzer that strips away the oxygen in the same way as the direct reduction iron furnace does today, and you would produce metallic iron product and oxygen on the other side. And this is something that Dara is working on now, and I'm planning on doing an experimental demonstration on this. Similarly, cement. There are many people working on production of lime, electrochemical lime production. So again, the problem with cement is you start with limestone. Limestone has CO3 in the molecule. So when you convert limestone, you emit CO2. So if you use electrochemical pathways to produce lime, you can solidify that CO2, so produce products that are solid instead of emitting CO2 in gaseous form. So that's one of another advantage of using highly selective processes. All right, I'm going to conclude with this summary slide. High temperature electrochemical systems, I think, are interesting because they can be integrated with many industrial processes. They can operate at relatively high temperatures, so you can exploit heat, waste heat from industrial sources. They can be used to perform chemical conversion of some of the most difficult to decarbonize sectors in our society, as well as producing commodities like iron, like cement, like chemicals and plastics, because the catalysts and the sort of the knobs that you can turn are more than what you can do in thermocatalysis, basically. So that's my last slide, and I'm happy to take any question.
Thank you. We do have a couple questions online, so I'll read the first one here. I think it might be going back to where you talked about the conversion efficiency. So the question is, if you add the energy required for compressing, I'm assuming hydrogen gas for storage and transportation, how much does it change the calculated efficiency? And they said, in my industry, pumps and compressors are the major source of losses.
So the efficiency values, I'm assuming that it was related to these values, I believe.
I think that's where, yeah.
Yeah, so these include the compression efficiency. So, oops. So these two compressors here are included in the energy balance that I reported here. So those 18% efficiency includes that value. It really depends on the size of the system, and let's say how often you go in off design. So that's when you go off design, electrochemical devices generally increase their efficiency. On the other hand, compressors and other mechanical systems usually don't or decrease their efficiency. So on an yearly basis, the effect of inefficiencies of mechanical systems is more important when you operate in off-design conditions. So it really, the answer really depends. But for these numbers, I included the compressor losses.
Any questions in the room here? Let me bring the mic over so online audience can hear.
In this superheated stream, what generally is the temperature and what is the feed? Is it water? Or
sorry, say it again.
For this superheated stream or like other SOIC cells, like when we are integrating with the discs.
Yeah.
So what is the feed for that? Like just heated water or?
Yeah, processed water. So in this case, water is recycled. So in this configuration here, liquid water is condensed and then recovered and recycled back. But there's always going to be some makeup water. So that input water is you start with ambient temperature liquid water, and then you evaporate it into the parabolic dish.
And how big is the effect of the temperature in these kind of operations? Like, is it like if we go very high temperatures, like then efficiencies go very high, or it's just like there is a threshold value to which it impacts?
Thermodynamically, it will continue to get better and better, but then it's a cost sort of effect. In general, the costs of high temperature systems is affected, but because these systems are generally more complicated in terms of their balance of plant compared to low temperature ones. So there is certainly, if you increase the temperature, there is a negative effect on cost. So there is a trade-off there.
I was asking from this same for the hydrogen production perspective as well, like for SOC feed perspective, when we are feeding like high temperatures, these high temperature cells on that perspective, if we are increasing the temperature.
Yeah, the thermodynamics says that it will be even better. Yeah, from a thermodynamic perspective, you will keep on increasing the heat input and therefore reducing the electric input for the same amount of hydrogen you produce.
Thank you.
Yeah.
All right, I'll look at the next question online here. Someone asked about the Pabara iron ore mine in Western Australia is the largest mine in the world, and the world's largest hydrogen generator is being installed there to power their trucks. This hydrogen plant is powered by a solar farm of 100 square miles or so. Would you know the process used here for hydrogen production? And if so, can you talk about it?
For that specific plant, I don't know. I assume that if it's hydrogen produced from electrolysis, it will probably be a polymer electrolyte membrane electrolyzer, which operates at low temperature. So those are not thermally integrated systems, and they are, again, a little bit less efficient than the one that I mentioned, but those are more commercially available than solid oxide.
In your SOEC, what is the electrolyzer? Is it something that contains like, what is it made out of, I guess?
So the material, you mean?
Yes.
So the electrolyte is a ceramic membrane. It's a dense ceramic membrane. The conventional material, it's yttria stabilized zirconia. So it's zirconia with some yttria in it. And so it's imagine like a fully dense, very thin ceramic layer. And then the two electrodes are mixtures of ceramic material and metal. So the cathode, the red layer here, is a mixture of yttria stabilized zirconia and nickel oxide. So that is usually called a cermet because it's a mixture of a ceramic and a metal. The anode side, the air side, is usually also a composite material that and it's usually chosen for its oxygen conductivity properties, because so these materials must conduct ions very well, but they also need to conduct electrons quite well. So the choice of the material themselves is dictated by the conductivity targets that you need at which temperature.
Is the industry already set up to manufacture these at a larger scale, or are they to manufacture these systems?
Yeah, so these are manufactured very similarly to batteries, so solid state batteries, or the manufacturing processes are quite similar. So we know that batteries can be scaled up quite well and economically. So these systems can use similar manufacturing processes.
I guess a general question online is, when do you expect commercialization for a lot of these systems and devices, and sort of breakpoints for initial costs?
So I mean, these systems are already commercial. The SOEC, there are companies that commercialize SOEC systems. Those that are not commercial are the one that I showed in the last 3 slides, that where the product is not just hydrogen. The product can be a fuel or a chemical. Those are certainly not commercial. Those are very, very much at the laboratory scale. In terms of costs, I don't remember if I have cost slides in this presentation. I do. So in terms of costs, so for SOEC, you can see the orange line here. Today, we are at about $2,000 a kilowatt. And the predictions is that it will go, it will decrease with the same function, same cost curves as solar PV 20 years ago, or lithium-ion batteries 10 years ago. So they are all electrochemical devices. The cost is always dictated by the area of the cell. So the cost functions, assuming that the manufacturing capacity of the market increases, the cost function will decrease with the same cost curves. So the cost curves, if we apply the same cost curves, it will reduce at 2050 to about $300 a kilowatt, which is the target of DOE. So the target for DOE for SOEC systems is $300 a kilowatt. So that, of course, is very much dependent on the increase of manufacturing capacity of the current OEM.
So I guess alkaline and PEM, they're considerably cheaper than SOEC, and they're more commercially used, but they're less efficient, right?
Yeah.
So what makes SOEC significantly more efficient is just the addition of heat?
Yeah, so if you work at high temperature, the kinetics are a lot faster than at a low temperature, ambient temperature. And that gives the higher efficiency to SOEC. Also, the other advantage related to this is that SOEC don't need noble metals as catalyst. So if you work at low temperature, the kinetics are very slow, and therefore you need an electrocatalyst that increase the reaction rates for your water splitting reaction. So PEM and alkaline need an electrocatalyst. So PEM must use iridium and platinum as catalyst to increase the reaction rates of the process. So on that side, on the PEM research side, the goal is really to get rid of or reduce the loading of that catalyst, because that is their main source of cost. But in terms of efficiency, it's simple sort of kinetics. If you work at higher temperature, these reactions happen faster, and so you don't need a catalyst.
And then the other caveat is that you need green renewable electricity inputted in these SOEC systems. And I mean, there's green steel operations going on. It's just a question of how much renewable electricity is available
right,
at a reasonable cost, right?
Right. Yeah, and the scale of this is enormous when you think of electrifying steel. So the typical steel plant produces 2 or 3 million tons of steel per year. And so the calculations we're doing for the project, the study that I showed earlier, we are calculating that you would need between 500 and 650 megawatt of electrolyzer for one steel plant to produce the amount of hydrogen needed to decarbonize that steel plant. So you would need, yeah, that's a lot of electricity for one steel plant. So that's what I'm saying, that if you didn't have that, though, then you would need to directly electrify the steel plant, but the amount of primary energy is the same, or it's very similar. So and then there is also there is a question of land use and footprint of these systems. So where are you going to put the wind farms or solar panels that have that size to decarbonize one steel plant? So it's not I don't have an answer yet. So we need to do the math and understand what is the best solution for this. It's still an open question.
Thank you.
to kind of go along with that, some of the implications environmentally of these systems, what is the feedstock as far as water? What's a requirement for the water feedstock for these?
So for high temperature electrolyzers, there are fewer requirements in terms of water purity. For low temperature electrolyzer, you need deionized water. So the any water resource needs to be very much purified before feeding it to a low temperature electrolyzer. For high temperature, you can use tap water, but of course that degrades the electrolyzer faster. We've tried testing electrolyzer with seawater, and it worked. We didn't test it for many hours, but we didn't see a lot of salt deposition on the cell. We did see sort of conductivity increasing downstream the electrolyzer. So that project is still ongoing, but the idea of using lower grade water resources is a big one. It's an important question, because of course you don't want to be a competitive for hydrogen production to agriculture or potable water.
I guess one more question online, and maybe someone was looking at your website. The question is, how is your high steel project going, and is the process of that project laid out in your presentation?
Yeah, so the high steel project is the one that I mentioned. The high steel project is this one here. So the project is ongoing. We are entering our third year of project, so it's the last year, and the last year is basically dedicated to the construction of the demonstration unit. We are working with an electrolyzer manufacturer that will build the demonstration unit at their site, and in this project, we don't have a steel manufacturer as a partner. So the furnace or the steel production portion of the schematic will be simulated in a hardware-in-the-loop demonstration with the electrolyzer. However, I have just submitted a few months ago another proposal for a phase 2 of this project in collaboration with the steel manufacturer, where we will, if awarded, we will go to a steel plant and deploy an SOEC at their site. So this iSteel is going well. I'm just hopeful that we'll get the phase 2 awarded so that we can actually demonstrate it in a steel plant.
Great. I think that's all the questions we have. So thanks again for your presentation and for answering our questions.
Great. Thank you.